Okay, I'm gonna try and explain this to the best of my ability. There's still a lot more you could add to this thing too. So I'm gonna call this glycolysis. This guy coming down, DHAP and GA3P. This is the prep phase, splitting phase, and then this is the energy phase. Okay, and we end up at acetyl-CoA, trying to pitch you back into place where we would know. Okay, so this is about interconversions and gluconeogenisis. So there's a couple things that are thrown into glycolysis, and then gluconeogenisis is using fats and proteins and things that are located in the TCA cycle and coming back up to make glucose, okay? So let's talk about them real quick, and then I'll try and explain the enzymes, because the enzymes are probably the trickiest part about this. So galactose, it requires 1 ATP. It's found up here on the diagram, galactose. It's found in the liver, red blood cells, and has in other cells as well. And it's kind of close to the glycogen, but in the notes, this is just a little bit more than what you need to know. But from the notes, it goes from galactose to glucose 6-phosphate. That's really all you need to know, is that it jumps from there to there. You don't need to know these interconversions. So from here, then it could use it however it would like. It could shoot it down. If it wanted to use glycolysis, it could go back up into glucose if it needed to, but we'll talk about that later, okay? So that's galactose. Fructose is over here, and this requires 2 ATP, and it's a 6-carbon molecule, and you'll notice that we're shooting it into the splitting phase. So this was the prep phase, right? So we didn't need to mess with galactose's carbon structure, but here, because this is 2 3-carbons and this is a 6-carbon, we have to break it into 2 3-carbon molecules, so it makes one of each. A side note is we talk about the polyol pathway, and that's when glucose goes to sorbitol and then to fructose, and this is used for sperm in the seminal vesicles. So just a random note, but it's obviously important to know because fructose gives energy to the sperm. So some other things is that it breaks the molecule into 2, and that it's found in the liver. Okay, so I'm not going to talk about that yet. So let's talk about anaplerotic and anabolic, and what that means. So the best way to describe this is, as soon as we get down to acetyl-CoA, this TCA cycle, it can shoot off and go into fatty acids. It could make amino acids if it liked. It could make cholesterol. It could make heme and porphyrins. BCAs will actually come into the TCA cycle. It can make other amino acids. So the gist of it is that things can come in and out of the TCA cycle. For example, we know that citrate goes to fatty acid or fatty acyl coenzyme A, and then it can go up. Let's actually just talk about that. So we can get 3 fatty acid acyl CoAs, and they come up through, I think, malonyl or whatever, or the mags or whatever it is, and they become triglyceride. But to become a triglyceride, we need a glycerol, and that comes from the DHAP. So glycerol and these two combined, we can make a triglyceride. So that can feed this system, and that's important if we're trying to make glucose. But this part is probably the most confusing part. It's gluconeogenesis. It all starts with pyruvate. Okay, so from pyruvate, we need to enter the mitochondria, right? And so we enter the mitochondria and we make OAA. And the enzyme that we use is called pyruvate carboxylase. And the tricky thing is OAA has a hard time leaving the mitochondria. So typically it has to change into something else. So it can change into malate, and then malate can change. As soon as it leaves the mitochondria, then it can change back to OAA, and then it can use pep carboxykinase to turn into pep. We could straight up go from OAA while we're in the mitochondria and turn into pep by that same exact enzyme, pep carboxykinase, and then we could leave the mitochondria. We could also go to amino acids, and then from the amino acids, we could turn into pep. So the long and short is that there's a lot of ways to turn into pep, but we need to get back from pyruvate to pep. And there's, I think like 4 routes that we could go. But from pep, you can see all these reactions are reversible, so we can go all the way up pretty much until we hit fructose 1,6-phosphate. And so to go from there, we just use fructose 1,6-biphosphatase, I think is what it's called. And that would push us to fructose 6-phosphate. And then we could use this reversible reaction and go to glucose 6-phosphatase. And that would push us into glucose. And then we could administer the glucose throughout the blood, get it to the brain, do what we need to do. I think the last thing that we need to talk about, there's still a lot more in the notes and you would want to go over them, but we have this fructose 2,6-biphosphate. It's in pink here, and there's some hormone regulation with it. But what it does is this is kind of like a stoplight or like a door opening and shutting. If we have high levels of this enzyme, it means that we could push down and go into fructose 1,6. If we have high levels of this, it means that we once had high levels of glucose, which means that we should have insulin involved as well. So that's why if we have high levels of this, then we're gonna have high levels of insulin. And the same would be true for the opposite end of the story. So if we have low levels of this, that means this is not glycogen, this is glucagon, excuse me. So if we have low levels of this, so low levels, which means that we are kind of low on this end of the pathway, then what we need to do is it will trigger glucagon, and glucagon will start to break things down here, and it will allow, so glucagon will allow fructose 1,6-bisphosphate to jump up. So this is like, it's almost a regulatory step, but so glucagon just jumps this guy up. So this would be in like a fasting state. We'd want to jump up, and this would be, this portion would be in a fed state. And it's just determined by fructose 2,6, where insulin or glucagon can play with it. So that's pretty much the interconversions. Like I said, we could completely go off into fatty acids. We could do a lot more. So we could talk about amino acids and the urea cycle and how they break down. But this is pretty much the gist of things almost.